Welcome back to the lecture. In this lecture on the introduction to molecular spectroscopy, we shall look at the interaction of radiation with matter a little more in detail. But first, I would like to impress upon you why we need to study spectroscopy in such great detail. There are many reasons, and I have listed some of these things. Since this is largely text, I have them already prepared as a text material. So why do we need to study spectroscopy? Many reasons. First of all, spectroscopy is the experimental science for understanding most of the developments of quantum mechanics, the theories, the predictions, etc. at one level. But from the point of view of chemistry, spectroscopy is the subject through which we are able to identify and analyze molecules and also new molecular compounds. So the entire branches of analytical, organic and inorganic chemistry laboratories all over the world, they use spectroscopy for several reasons. Obviously to identify new compounds, to identify intermediates in a chemical reaction, because very often if the intermediates are slightly long lived, it is possible for us to actually detect them using several spectroscopic techniques depending on the lifetime. It is also important in our ability to understand how a chemical reaction takes place. Therefore, predicting the reaction mechanisms is an extremely important objective and an activity of any chemist, particularly organic and inorganic chemists. In the physical chemistry laboratories, of course, we use molecular spectroscopy to obtain signatures of molecules. That is, what is a molecule in terms of its size, shape, the bond lengths and bond angles between different elements in the molecule, and therefore the entire range of molecular structural parameters, molecular geometries and molecular properties, the electric and magnetic properties of the molecules can all be studied by using spectroscopic techniques as well as the quantum mechanical and physical chemistry theories. So the energy levels of molecules, of course we cannot measure the energy levels, but we can measure the transition between the energy levels in the form of the light that is absorbed or the light that is emitted. Therefore, transition frequencies can be experimentally observed, which validate the calculation of the energy levels. We can study molecular electric properties such as the charge distribution in a molecule. If you think about carbon dioxide as an example, carbon dioxide does not have an electrical charge distribution which is polarized. That is, the carbon at the center with the two oxygens, the positive and the negative charge centers coincide in terms of the electronegativities, and therefore carbon dioxide does not have any electric moment. At the most elementary level, it does not have a dipole moment. On the other hand, if the carbon dioxide molecule during vibration is slightly bent, you can see that the carbon oxygen bond may have an electric dipole because of the carbon being slightly positive and the oxygen being slightly negative. There is a charge separation and there is a distance between them. Therefore, the charge times the distance gives you the dipole moment, and correspondingly on the side there is the other dipole moment, and these two dipole moments being vectors actually add up to give you a net dipole moment. This is during the process of molecular vibration. Therefore, it is possible for us to identify electric dipole moments which may not be there but which may appear. That is in the case of a molecule such as carbon dioxide. On the other hand, if you think about say methyl chloride CH3Cl, you know that the carbon chlorine is one of the tetrahedral bonds and the carbon hydrogen is the other of the three tetrahedral bonds that you have, and therefore there is a net dipole moment in the molecule. And such molecular charge distributions due to the atoms in the molecule are measured in the form of electric dipole moments, and they are measured in the form of quadrupole moments, and also in the field of an external electric or magnetic field, how these charge distributions rearrange themselves, they polarize themselves in the form of what are known as the polarizability factors. So, molecular electrical and magnetic properties are directly studied by associating the electric and the magnetic fields of the electromagnetic radiation with such properties, and then determining them, the changes that happen and so on. Molecular geometries are fully determined by calculating the moments of inertia, the center of mass in the molecule, and then the moments of inertia about 3 mutually perpendicular axes, and then the nuclear magnetic moments of the individual nuclei, the fine structure constants such as the chemical shift and the spin coupling constants that you will eventually come to know of in nuclear magnetic resonance and so on, and there are many other fine structure constants. Therefore, physical chemistry is very much concerned with determining the entire range of properties and distribution of electric and magnetic charges in a molecule. Therefore, spectroscopy is very important. Atomic spectroscopy, of course, is the experimental method, is the experimental technique from which much of quantum mechanics evolved. You remember Niels Bohr trying to explain the spectrum of the hydrogen using the already known series of spectral lines known as the Lyman series, the Balmer series, the Paschen series and so on. And Niels Bohr came up with the first the idea of what is called the quantizing the energy of the electron in an atom, and therefore atomic spectroscopy since then is one of the most important branches for understanding quantum mechanical concepts and also experimentally the behavior of atoms in magnetic and electric fields. Molecular spectroscopy, of course, permits us to study the chemical reaction dynamics at the most fundamental level, and as the atoms move away from a molecule, they either dissociate from a molecule and form other species and so on. If you want to follow that in detail, molecular spectroscopy provides you much of the answers. So, as a field, spectroscopy has matured to give you many answers. Now, it is not all happening through very simple processes. All of this does not happen by taking the electromagnetic radiation in any which way that we would like to, but understanding the fact that different energies, different electromagnetic radiations with different energies have different impacts on the molecule. First of all, how do we classify the electromagnetic radiation for spectroscopic studies? Here is one small table that you can see that gives you the type of radiation approximately in the corresponding frequency ranges, and also the wavelength corresponding to that frequency or the wave number corresponding to that. The most common unit of wave number is not a meter inverse but centimeter inverse. That is what you see in most textbooks. Of course, wavelengths are often described in nanometers or even sometimes micrometers. Frequency is always in the form of second inverse, and therefore this unit is known as the hertz. Cosmic radiation has a very high frequency, and therefore the individual photon has an extremely large energy. Gamma rays have frequencies in the range, this is an approximate range, in the range between 10 raised to 20 oscillations per second to 10 raised to 18 oscillations per second, and the corresponding wavelength, which is obtained from the relation I wrote down in the last lecture, is approximately 10 to the minus 3 nanometers to, that is, this is like a picometer, and then 10 to the minus 1 nanometer, and the wave number is about 10 to the 10 to 10 to the 8. X-rays are next lower in energy with a frequency between 10 to the 18 hertz to 10 to the 16 hertz, and the wavelength is between a nanometer to 1/10 of a nanometer. Ultraviolet rays are the lower in energy. Each photon, if you write E is equal to h nu, the ultraviolet rays has lower energy than the X-ray photon, and you see that the frequency is 10 to the 16 hertz to 10 to the 14 hertz, and the wavelengths and wave numbers are accordingly the numbers that you see here. This is an approximate division for the energies. And then visible light, which all of us are very familiar with and all of us are impacted by so much is actually a very narrow range of electromagnetic radiation frequencies. It is roughly between 8 and 3 to 10 to the 14 hertz. Therefore, it is a very, very narrow range in which you see all the 7 colors and also the range of colors, the visible light and the corresponding wavelengths and wave numbers are given here. These are important in understanding what properties that they allow us to investigate. Below visible light are the infrared radiation, microwave radiation and radio wave. Both microwave and radio wave are extremely important in studying magnetic properties of the nuclei, magnetic properties of the molecules, and therefore in the nuclear magnetic resonance and electron paramagnetic resonance, the energies corresponding to microwave and radio waves are typically used. And you can see that the microwave frequency is roughly between this is 1/10 of a gigahertz. A gigahertz is 10 to the 9 hertz, and this is about 1000 gigahertz. So you can see that this is the range of frequencies, and the corresponding wavelength and wave numbers are given here. And the radio wave is of course among the lowest in energy with a frequency less than a gigahertz. It's about 300 megahertz. That's what you have, and the wavelength is 10 to the 9 nanometers. That's almost a meter. That's why it's called a radio wave. It's a meter wave. Okay, so these are the typical classifications of electromagnetic radiation. But in the visible range, and in the visible and the UV, visible and IR range, there is further classification of electromagnetic radiation as far UV, near UV, visible, near infrared, mid infrared and far infrared, and these are approximately corresponding to the different types of interactions that the light will have with either the electronic motion or with the nuclear motion or with the overall rotation of the molecule and so on. Therefore, this is important to remember. The approximate numbers of the wave numbers are given here. The spectrum, if you look at it, the colorful spectrum that you have is actually only from far UV, which is somewhere around here, very high frequency, to the far IR, which is somewhere here, very low frequency. This is the visible spectrum, roughly between 8 times 10 to the 14 hertz to 3 times 10 to the 14 hertz. Now, why is it important? Because in each of these regions, as you see the radiation from cosmic rays to radio waves, the molecular properties which are probed by the radiation are different. What are those properties? You can see that list below. So radio frequency, now we go the other way around. Radio frequency is the lowest in energy. Radio frequency enables us to measure what are called the nuclear magnetic dipole moments, and therefore the magnetic dipole interactions between nuclei, dipole interactions, and also the nuclear spins, how do they couple with each other through scalar and tensorial interactions, and then the electric quadrupole moments, which are basically charge distributions inside the nuclei, which are non-spherical charge distribution. That is, the nucleus is not a spherical nucleus, but it's slightly distorted, and how these non-spherical charge distributions interact with non-uniform charge distribution outside due to the electrons, and those are called electric quadrupole moments. These are fundamental properties of many nuclei, all nuclei with the spin quantum number 1 or more. All of these are measured using radio frequency and microwave region, and both these basically what we call as the magnetic, these are what we call as the magnetic resonance spectroscopy. Microwave, of course, can also be used to measure the molecular moments of inertia and properties known as rotation constants, from which it's possible for us to determine the equilibrium structure of the molecule, and through the equilibrium structure we may also be able to calculate molecular electric dipole moment and the intensities of the radiation in microwave. Therefore, properties of the molecular structure and molecular electric charge distributions and the electronic magnetic dipole moment, all those things are measured using microwave spectroscopy. Infrared region allows us to determine the bond strengths of most molecules, stable and not so stable molecules, the extent to which the molecules can be polarized by external electric fields, distorted, and the force constants which are roughly proportional to the bond strengths. All these properties can be determined using infrared region. The UV visible region allows us to understand electronic transitions in an atom, in a molecule. Therefore, the electric dipole moments are due to the electronic motion and the dissociation energies of the molecule. I mean, what energy is required to break the molecules into individual components, etc. And also the optical properties, visible optical properties that we make use of in day-to-day life, the luminescence properties of the light that you see here, the fluorescence property that you see here, the phosphorescence property, the screen for example is phosphorescing, and therefore that kind of electrical properties are studied, those kinds of electrical properties are studied using UV visible electromagnetic radiation. X-ray region allows us to understand the core electron energies inside the molecule. In an atom, for example, if you have say a sodium atom, you know from the elementary electronic structure that it has one valence electron and has 10 core electrons which are in the 1s and 2s orbital. Transitions between them can be studied using X-ray region because these are very high energies, and also X-ray is extremely important for surface properties and surface analysis, particularly in solids and in crystalline materials and so on. So surface properties and characterizations are very usefully done using X-ray spectroscopy, and gamma ray region, which is due to the gamma rays which are extremely high in energy, allow us to study the nuclear properties such as the nuclear quadrupole moment and the chemical shift or the isomer shift that we need to know. So these are some of the properties which are scaled by different radiations of energies, and therefore you can see that electromagnetic spectrum with 15 orders of magnitude in energies between say 10 to the 20 hertz for the cosmic rays to about a megahertz, 10 to the 6 hertz in the case of NMR, that is magnetic radiation, magnetic resonance, the nuclear magnetic resonance. The 15 orders of magnitude scale the entire molecular properties, and therefore it is very important for us to understand each and every one of them in detail. Of course, this course will give you an overview of some of these in the case of microwave, infrared and electronic spectroscopy. I will not be dealing with magnetic resonance in this particular course, but in a separate course I will give you more details. Okay. We will continue this to understand a little bit more about what are the features that we look for in a spectrum in the next lecture. Until then, thank you.